Welcome to the lecture on Chapter 14, CS 1030, Programming 1.0. This will go along with the next chapter, Chapter 15, which is Programming 2. And together these will help with the programming assignment that we've discussed in the introduction to Chapter 14, and I introduced in the introduction to Chapter 13. So please refer back to those or in the Assignments tab on Canvas for more details. So here are the objectives that we're going to cover in this chapter. We're going to learn what it is and how it's developed. Now, this is specific to the languages we talk about here, but the fundamental underlying philosophy of this lecture really kind of applies to all programming languages. We are going to talk the difference between low-level and high-level language. Most of you will probably develop in a high-level language. Low-level languages, really the lowest being what they call assembler, is called closer to the metal, are a little bit harder to program in, but we'll talk about the differences between them, and we'll look about programming structure. We'll take some time on algorithms and a little bit on pseudocode. As you know from my Chapter 13, I'm not a big fan of pseudocode. I figure if you're going to write pseudocode, either make comments in the code or just write the code itself in order to get what you need done. We're also going to learn about what a variable is. For those in the CS 1400 class, this is going to be a rehash, so please bear with me, and how they're used. Really, variables is what makes a program useful, because it allows for different types of information to come in to be worked on. If you didn't have a variable, then you would have a straight run program and you would have to write for every single possibility. And just imagine, if you will, if you didn't have a variable, say on a program with a checking account, how you would have to write for every possible value. If you were depositing even between $10 and $20, you'd have to account for every single value, like $10 and $10 and a penny, $10 and 2 cents, etc. We're going to talk about control structures, which make programs even more valuable because now they can take different actions based on the information that they get. And then we're going to have a very brief introduction to object-oriented programming. There is courses on OOP, as it's called. It's a good fundamental basic understanding of how to program, and I highly recommend that if you are going into development to at least get a good basis in object-oriented programs so that you understand the concepts. So, what's a program? Well, in this day and age, just about everything that you use or interface with in some way or another has a program behind it. We've talked in previous chapters about the GUI, which is the part you actually interact with. This one we're going to talk about the plumbing or the behind the scenes for the program to get things, that GUI, to actually get the machine to do things you want it to do. So some examples they have here are cars. Cars come out and they become more and more sophisticated. There's a lot of development that goes in to those cars. For instance, I was reading an article about Tesla, and I know that there's at least 1 to 2 million lines of code in their cars for the programming of the car, and I'm sure there's probably more now. But think about that one. That's a lot of code. The space shuttles, any of these flights, any of these, the James Webb Telescope, for example, or any of the satellites getting into space, have lots and lots of programming to control thrusting and vectors and all the controls and the direction, servos, etc. All of that's done. ATMs, of course, ATMs come out. We kind of take them for granted now because they're just about everywhere. But again, when ATMs came out, they were trying to program a replacement for a teller who sat at the window. But then you don't need to think about things as complex as ATMs, space shuttles, and cars. Even the simple things like a microwave has programming behind it. Just think about that. You got a very simple interface. You got a couple of buttons that are pre-programmed to maybe set the duration and the intensity for defrosting, for example, or power levels. but it's a very simple interface, but it still has a program running behind it to activate when to start and stop and kick on the microwave itself and to notify you when things are done. So all of these have programs behind them, and it's now getting back down to the IoT, Internet of Things devices like Raspberry Pis, Arduinos, etc., that the programming is getting smaller and smaller. Again, it's kind of seemed like got away from the bare metal programming and went to high level programming, and now it's going back to bare metal again on some of these, uh, really using programming languages like C. And even though C isn't necessarily low level, right next to the metal, it's still pretty close. And so a lot of that's going on as well. And you have devices that are very small in size that are taking kilobytes of data to run. It's quite amazing. So, and the second bullet point here seems to be understated. It says it's important to develop a quality programming product because people depend on it. Well, although it does seem to be understated, it's quite important because how many apps have you used or tried to use that may have done everything for everyone, yet their interfaces were horrible, or they were buggy, or they crashed? There's numerous examples of operating systems that have come out and crashed because even though it appeared to be quality, they were exposing a lot of bugs. So when you are writing a program, the number one goal in mind should be to write as quality a program as possible while meeting the goals like we talked about in the software engineering chapters, but understand that people are going to depend on this. And so you're putting your heart and soul into a program. You want it out there, understanding that people are depending on it. In this day and age, if people cannot depend on your program, they'll drop you and they'll walk to something else. It is amazing. Studies have been done that people are willing to actually go with less features for a more dependable program than a program that promises to deliver everything and yet delivers on nothing. So again, quality should always be your number one goal, and especially when you get down into real-time systems or critical systems like something for, say, a health monitor. You want to make sure that those can be depended on to report accurate data. And then if you are going to get into programming, just about every aspect moving forward of computer science, the understanding of programming is essential in career. It may not be something that you choose to do for a living, but it's essential to understand how a program works, how it gets put together, so that if you're going to develop it, great. But if not, you can at least understand how it works, so that you can address that with other people in your company and become valuable. So what's a program? Program is simply a series of steps that you tell the computer, this is what I need you to do. Now understand, computers are stupid. We call them smart, but they're stupid. Computers do exactly what they're told. There's an adage in here that I'll probably repeat numerous times when you're developing. It's called garbage in, garbage out. We talk about artificial intelligence. We talk about how computers are smart, but really all the computers for artificial intelligence are just taking a lot of data and using the processing power behind it to infer results. But really, when it comes down to it, they do what they're told to do. And so when you put in a program and you expect it to add two numbers together, for instance, and those two numbers are not added together correctly, it's most likely, unless you found a bug in the software or underlying OS or something, it's most likely your code. And so if it is your code, the computer's doing exactly what it's told. So it's a series of steps, and this is where an algorithm comes in. The algorithm is the series of steps you tell the computer to get to the end result. It is used to solve a problem. Usually, if you're a good developer, to solve a specific problem. They may come in and tell you, hey, we want this program to do all of these things. But when you're programming, your aim should be, at least, in portions of the program, to solve a very specific problem. You do that with an algorithm, which is a series of steps on how to get from point A to point Z. So it solves a problem, and then the program itself is compiled down to machine code. Now remember, machine code is zeros and ones, and as you remember back into some of the other lectures about the CPU, zeros and ones translating to turning on and off certain circuits and pulses through the CPU, and it's those pulses and those memory reading and steps that we're doing here, turning the certain transistors on and off, that actually end up as what the computer does. So that is done by the compiler program. Generally when you're developing, even if you're developing an assembly, there's still a compiler to translate that down to zeros and ones. So then you'll have what they call an interpreter, which will translate the statement into a language the computer understands. Now the interpreter is also called the compiler, and that is what it says here, convert into a language the computer understands. That's done by the interpreter or the compiler. Now, not to get too technical, all programs get interpreted into machine language. Some of them get compiled directly, and others of them get compiled into an intermediate language, which then are on the fly interpreted. Programming languages such as Java and .NET and Python are interpreted, meaning that they don't compile down to machine code. They compile down to an intermediate language, which is then converted rather quickly to machine language. Programming languages like C and assembler get compiled directly into machine code, like EXE, which can be run directly on the computer without having to have the intermediate. Like in Java, it's called the JVM for the Java Virtual Machine, and for .NET, it's the .NET Missile code, as it's called, that have to have surrounding interpreters to compile that. So that's just a small difference here. And that's here talking about the compiler. This is what actually puts that information in. Notice here it says it produces an executable file running independently of an interpreter. So again, I want to stress the difference here. An interpreter is what they call compiled to intermediate code, either JVM or Missile for Java or .NET respectively. And then as those pieces of program are needed, they're translated down into machine code. When it's compiled, it's actually compiled all the way down to machine code, and you theoretically could take that EXE program, go from one computer to the next and run it without having to have any converters or transpilers or anything. And so C programs are a good example of doing that. Programs are developed to help perform tasks, and computers are really, really good at performing redundant tasks. Humans, I mean, we can go insane having to do the same thing over and over and over again. It's not what we're really rigged for. Become monotonous, and then your mind begins to wander, and then you begin to slip. And so that's why in the early days of assembly line work, through the day, they noticed that towards the end of the day, towards the end of the week on the shifts, that quality was slipping, and that's because the redundancy of doing the same thing over and over, people get bored, they get sloppy, and so computers, they don't. That's what they're really good at doing, is just the same thing over and over. And so they help us get jobs done that we don't want to do ourselves. They'll do it the same way every time with the same results. They're not prejudiced, which humans are prejudiced, and that's why I always think it's funny when people are playing a game and they keep accusing the computer of cheating. Oh, the computer's cheating. Well, the computer's not cheating. It's doing exactly what it's told to do. There's no prejudice on there. It's just working within the confines of the program. So what could cause failure? Well, lots of things can cause failure. You can leave important logic out. Your algorithms are not complete. Inadequate testing, bugs, logic errors, which we talked about in the previous chapter. There's also hardware failures that can cause a program to fail. There's a lot of things that can cause program to fail. Now, there's actual fails and then perceived fails. Perceived fail is the program is actually running correctly. Again, they're stupid, did exactly what you told it to do, but logically you forgot some steps. So naturally, people are going to say your program's broken. So understand that when they say that there's a program failure, that doesn't necessarily mean the program doesn't run and perform tasks. It may not be performing the right task or the full task. But there are times when there's catastrophic failure in the hardware and the program can crash. And we've seen those for those Windows developers, or people who've worked on Windows. You've seen the blue screen of death. And a lot of times that can be caused by actual hardware failure. That happened to me. I had a stick of RAM which was corrupted, and occasionally when that memory was being accessed, it would cause a blue screen of death. So the software was actually running. It was the hardware that was causing the failure. So, first step in programming is determine which language you want to use. Now, before, you used to get a language and stick with it. And I can tell you right now, that is not the way it goes in programming. Most programming jobs right now, you have a base language you've started on, whether it be something like C Sharp, you know, maybe Visual Basic or VB.NET, maybe Java, maybe Perl, if you get into that, or maybe Python, which is really starting to make a surge right now. It could be something like C. So you get into a language and you decide which language you're going to use, and you learn the way to program with those languages. Now, each language you can think of as like a foreign language that you would speak. They generally have a set of rules in which you work in, grammar rules, and then when you learn them, it's just learning the words within those rules. Programming is similar to that, and like I was saying just a little bit ago, very rarely do they now ask for a programmer who only knows one language. Generally, they're asking for programmers who know a variety of languages. So, for instance, you may see a job in which they want C Sharp as the primary language, but they may also ask for skills in JavaScript or in SQL for database development, and they may ask for other languages like being familiar with Java and maybe Python. So before you look at it and say, well, I have to learn all these languages, you don't. Generally, the field of profession you're going to go into will help dictate that language. So if you're looking for more close to the metal, like writing drivers, or you're writing the next greatest physics engine for a game or what have you, you're going to maybe go to C and assembly. Electrical engineers have a tendency to go down to C because they program closer to the metal. But a lot of developers who come out and are developing business applications, or they're developing apps to run on top of the Apple iOS or Android, they will be using something like Java, or they might be using a programming language called Rust, or they could be using C Sharp. There's a lot of languages, higher level languages. So I can't tell you which language is best because all languages have strengths and weaknesses. There's not one language out there that rules them all, although there are people who believe there is. There are some languages that have really been developed for a very specific set of instructions, and they do it very well. Now, you can, through coercion or really good programming, extend that, but at what point does it make sense to try to force yourself to use a language that's not really written to do what you want it to do versus going and learning another language? So as we talk about programming here, we talk about the basics of OOP, and we talk about, as I'll discuss some of the other standards out there like REST APIs, for instance. Most of these programming languages support those standards that are out there, like TCP/IP. Most of these languages have a TCP/IP stack to develop against. And so some of these languages are really great for writing GUI applications. Others are not. And so, learning the basics of how a program works and OOP and using standards, then it's simply learning the syntax and maybe a few idiosyncrasies of the programming language so that you could pick that up. So the intent here is not to say this language is better than that language. The intent here is to say this is how you program, and now go out and learn how to program in the language of choice. So low-level languages, it's machine code, binary, zeros and ones. Most people don't program in machine language because it's zeros and ones. We're not really geared to doing that. That's what the compiler does. That's what the interpreter does. So really, right above machine language, which is right on the metal, as they call it, is assembly language. Now, assembly language is just one step above machine language. And instead of having to write out all the zeros and ones, you have a series of codes or instructions that then are compiled down to zeros and ones. So it's similar to taking, for instance, binary and converting it to hex. It gives you a much shorter representation of what the machine code or the binary code is underneath, excuse me, but you have it in hex, so you don't have to write out all the zeros and ones. So assembly language is still used today. It's still very powerful. It's used a lot in graphics engines where you need to get down to the metal, and it's also used in a lot of real-time systems where it's critical to have as much control over the bottom of the programming, meaning the registers and reading, than having layers above that doing it for you. So assembler or assembly, they're both the same thing, is the assembler is that the program that reads the assembly language and converts it. It's the compiler. You will often hear people say assembler and assembly interchanged, but those again, and we'll look at what some of this code looks like, but it is very quick compile, very small compiles, but I knew a gentleman who was writing a piece of software for small airplanes that would detect the G-forces and send off an alarm if the G-forces were too high. And I was looking at his code, and this is way back in my very early programming career, and I looked at the assembly language he was programming it in, and it was so foreign to me, it made no sense. And as we look at some examples, you're going to see that it is very kind of abstract from some of the higher level languages, which we'll look at. Now, the higher level languages it says more natural language that we can understand. Let me put a caveat in that. It uses words that we're familiar with, but that doesn't necessarily mean that people can read and understand it. There's still a syntax, there's still rules. But looking at the difference between assembly and high-level languages, you're going to see quite a marked difference, even between assembly and C, for instance. It's a little bit easier to understand what's going on in C than assembler. So here's our programming languages here. So when I say it's closer to the metal, that means right here. This is the machine, the actual physical hardware. It's the metal. Right above that is the machine language, zeros and ones, which most people aren't going to program in. For those who want to get close to the metal again, they're going to start here with assembly. Now, don't think that a high-level language gets converted to assembly language and then gets converted to machine language. That's not necessarily what it's showing here. What this is trying to show is that the high-level language is highly abstracted from the hardware, meaning that it's got to go through an interpreter or a compiler to get down to the machine language to tell the hardware what to do. So you'll notice that the more you go down, the more archaic the language is going to look. So very few people code in machine language. Most people start with assembler. And the big thing is it simulates machine language, and that's the key. It simulates it. It uses English-like statements, but not, I mean, it would be English-like statements for somebody who talked in all, shortened sentences. Everything's cut off. you know. But it does, I mean, the big one here is each instruction corresponds with one machine instruction. So when we take a look at this, you're going to see that every line that you see in there is translates to one machine instruction. And that's the power that you have with assembly language, because now you're telling the CPU exactly what to do step by step. And as it says, they're smaller and faster, and they're extremely powerful. Now, the flip side of that is they're generally tied to a CPU type. For instance, an Intel chipset is going to be different than another chipset that's being used for like IoT, because they have different registers and they have different instruction sets. So they generally, when you write assembler, you have an assembly or assembler for every CPU. So that doesn't necessarily mean that writing assembly for an Intel chipset is going to work for writing assembly for instance, like a Broadcom chipset. So, although the language is the same, the way you get to the end of an answer may be a little bit different. But they are powerful, they run faster, but at the same time, you're going to see that the actual amount of code to do some steps, you have to tell it in a for loop. You have to give it every single instruction in a for loop. And in a higher level language, you can use code words like for each, and then it will compile the language down to the individual steps for the CPU. So you can program faster in, I believe, in high-level languages, but if you want the ultimate control, ultimate power of what's going on, you're going to use assembly. So remember, we have registers in a CPU, and these are locations that the program stores and retrieves information. And we have 4 types of registers. We're not going to spend a lot of time in this. For those of you who get into electrical engineering, you'll probably spend some time in this. Or if you want to go out and say, hey, I want to learn assembler. I did some assembly programming a long time ago in school and never did it since, because I always found that I was able to get done what I needed to get done in the higher level languages. But you have AX, BX, CX, and DX registers, and most of these are done for math, because remember, all the computers are doing is math. Ultimately, when it gets down to the what is a computer doing, it's doing arithmetic operations to get to a result. And that's the zeros and ones, right? Binary math, we talked about that. And so we have these text instructions which will, one by one, convert it into binary. And that's the big thing I wanted to point out here, is that it is done one by one. Now, that's what the compiler does. Now, it's hard to read and understand. There are some rules for how the language statements must be constructed, and this is true for all programming languages. It's called the syntax. Most programming you do today, you'll do not in like Notepad, you'll do it in a development environment, and a lot of the development environments now have a syntax checker. So if you write in a command or an instruction in your program and it's wrong, then it generally will notify you that there is a syntax error. Now, it's not necessarily true of assembler, but a syntax error is a bug in the program which actually prevents the program from running. It will probably prevent the program from compiling as well. So most compilers will check syntax. So to move something, you use the move command. And so if you want to move a value into the CX register, this is right here. This is the command. You're moving into this register, and then you've got a comma here, and you're moving the value 8 in here. So this, looking at it, is I'm moving into a CX register 8. Now if I want to copy, I can copy the value of one register for the next, saying I want to move what's in the DX register into the CX register. So you can move values from point to point, but now as you understand that as you're moving values from one register to the next, Now you have to check your array bounds. You have to check to make sure that that value isn't contained. There isn't a value contained in there, because you can introduce subtle bugs if you're not checking these register values. You can inadvertently copy a value into another value and overwrite it. So if you're going to be doing an assembler or assembly programming, you're going to have to really pay attention to what's going on. You're not going to have the nicety of your, say, array bounds checker, or you don't have to worry in the high-level languages like C# and Java, well, which registers you're using, which memory locations you're using. The program does that for you. So using assembler, and some points using C and even C++, you are more responsible for where your data is put in the registers and in memory. That gives you both the power to control everything at a very low level. It also makes you responsible for that. So to add something, takes the value on the right and adds it to the value on the left. So first thing we're going to do is move into the CX register the value of 2, and then in the DX register the value of 8. And so this is how we add 8 and 3 together to get 11. So we have to give it 3 instructions. We have to say move the value into a CX register, move the value into DX, and then you need to add the value on the right here to the value on the left here. And so 3 steps to create one value. In a high-level language like Python, you could just do 8 plus 3 and it will kick out 11 for you. It doesn't matter if it's 8 plus 3 or it's 3 plus 8. You don't have to worry about which order it's, the value is added from right to the left. You're just adding it up in one line and it does all these steps for you. So you can see as a high-level language, you don't have to tell it to move values into registers and then add those registers together. But at the same time, using assembly, it gives you this ability to say, I want to move into this register this value. Now, most people look at this and say, oh, this is include. This is the kind of shortened version of include that we always see. In this case, it's increment. So you see here that we're adding DX to CX, and so we're adding this register value into DX. So now the value of DX was 8, and now we're adding 3 into 8. So the value here in the register DX is 11, and now we can increment that, and we can just increment that value here, and we get 12. So again, all of these, you have to tell it very specifically how to, where to put it, how to add it together, adding this register to this register, and that's important. If you swap this and added CX to DX, you'd still get 11 in CX, but if you incremented DX, you'd only get 9, because remember, it's adding the right to the left. And this is the rules, this is the syntax, this is the constraints you have within the programs. So where, again, in Python, adding 8 to 3 or 3 to 8, doesn't matter, because it knows where it's stored and which registers it's using. And then if you increment that by 1, it knows where it's storing that. So you have to be very careful in assembly language. So, of course, sub means subtract. So you'll notice here that add is ADD, which we're used to, and subtract. Well, this is probably okay, because sub, but can mean subtract, but it also in some languages means is identified as a method or a function. So again, when switching from language to language, they're going to use similar verbs to do different things. So that's another thing that you have to kind of keep in mind as well. So subtraction is going to take one number for another. So the example is we want to have dx, the value of dx, be equal to dx minus cx. So we're going to say we're going to move cx, we're going to move 4, we're going to move 7 into here. Now there's a couple of things to know here. when we subtract cx, because remember it's the right side from the left, so when we subtract cx from dx, dx is going to have 3, but cx is still going to have the value of 4. So that value is still here in the register. So that's some important things to remember, is that just you're really modifying the dx register and the value there. And again, it's a little bit different because you're subtracting this value from this value. The CMP is compare, and it does a little bit of comparison. Now, just as a small aside here, if you've made it this far in the lecture, note that there are no tests on or questions on the test that say what's the output of this assembler program. This is not a programming class. This is just an introduction to programming that's kind of giving you an idea of what to expect in a low-level language versus a high-level language. So if the syntax seems to be a little convoluted or something that you're not really wanting to do, that's okay. The overall aspect of this is just what's going on, how to talk to a computer. So, okay, back to compare. It compares two values. So notice here that the result sets flag bits in the FL register. So you're comparing two numbers, then you have to check whether or not the FL register is 0 or 1. Again, everything is binary, right? So you're going to compare two numbers. In a high-level language, you'll compare them and get back a true false or a 0, 1. If the result of the compare equals 0, which it's set to binary 1, and the sign flag set to 0. If the result is a negative number, which means they do not compare, then the flag is set to 0 and the SF flag is set to 1. So let's talk about this for a minute. We've got two flags. We've got the result flag, which is really what we're looking at here. If the result is 0, that means that, or excuse me, if the compared result is 0, meaning they're the same, then we set it to 1, meaning that that's true, they're the same. Otherwise, we set it to 0, meaning that it's false, and then the SF flag gets set to 0 or 1. So if CX minus DX equals 0, then ZR flag is set to 1. So we could say here, we're going to move CX into 4, DX in here to 7, and then we compare it, and the value of what's stored in this register here is going to be set to 1. Now this is the ZR flag, so this is saying that these are set to 1, meaning they're not equal. The JNZ is a value flag maintained by the system, and this is to jump someplace else in line. So if it's set to 1, it's kind of like a go-to statement. If it's not set, then it goes in line. Now, one thing to know about assembler is assembler moves from line to line to line. So it does moves the CX into 4, into this register, the value of 4, into DX, the value of 7, then it does a compare. It's all done one line at a time. Each line is a single instruction to the compiler, so it does these things one at a time, then it does the compare. And at this point, it says, hey, if the ZR flag maintained by the system is saying stop, that means this program is done. Otherwise, it continues to move. If it needs to move to a different part of the program, for instance, skip some logic, then it will move to a different location. Again, if it doesn't do that, each line is executed sequentially. That's all there is about assembler. We're not going to go into it much more than that. Just understand that assembler is very low level, that it requires you to do one instruction or one line per instruction, and that it is very close to the metal. It's something that you're going to get into maybe if you're getting into electrical engineering or writing real-time systems, or you need to get into some of these physics engines for ray tracing and so on. Alright, let's talk about high-level languages now. So this is important to know, that the high-level language writes the program independent of the CPU. So languages like C Sharp, especially with .NET Core as it's called in Java, they write to a virtual engine that those virtual engines are different for each system it runs on. So whether you're running in Linux, PC, Mac, on your phone, whether you're running some of these interfaces like on DVD players or running a JVM Java and so on. Some of these little IoT devices, fridges, etc. They're all using these virtual machines. So what's nice about it is you can write to the Java virtual machine or to the .NET middleware, and then it does the compilation needed to run it on the underlying operating system. So you don't have to maintain separate codes like you do with assembler. You can do a lot more with a lot less coding, because now instead of having to give every single line of instruction, what you do is you give the syntax and then those can, and say I want to do these steps, and behind the scene that is compiled down into machine language for each step. So there's not a one-to-one relationship between this instruction and this step. They say they generally run slower, meaning they have to be compiled or interpreted, but those disadvantages are becoming less and less of an issue as hardware becomes more and more robust and quicker. However, just understand that if you're looking at needing close to the metal, real time, you're looking at C and assembler. So some examples of high-level languages are Java and C++, which is just C with object-oriented. An older language is still hanging on for some reason. It's called Delphi. Delphi is based on a language called Pascal. And then, of course, you've got C Sharp. And another good example on there is Python, which is making a huge surge now, and especially in scientific data manipulation and artificial intelligence. So using an IDE, you program your language, and your IDE gives you a lot of advantages. It can help you with syntax error, it can help you compile, it can help you test, it can help you write code, less code to do more because there's a lot of keywords, and within the IDE you often have shortcuts that can produce a lot of code for you. You have things called like struts in Java, other classes that people have written that you can pull in and use, so you don't have to write everything one at a time, each line one at a time. The IDE should be there to help you write more effective code without having to worry about all the underlying changes that are happening in the compilation or the interpretation. So this is an old Microsoft Visual Studio IDE. This is VB, and it is, oh no, I'm sorry, this is C Sharp. This is an old version. The new IDEs for Java and .NET are much more sophisticated than what we see here. But what you'll have here, for instance, is you'll have some toolbars on this side here. Usually have, this is an ASPX page, you'll usually have a design page here where you're going to drop in some values, and you can see here, just by looking at it, that you can kind of infer what's going on. Over here you have your Solution Explorer where you're actually going to do your code. Here's some properties to set to change the colors, fonts, etc. And you usually have all these toolbars up in here. All of this, and Java's got something that looks a little bit like this. All of this up here is to help you code easier. So now instead of having to, like for instance in C or assembler, if you wanted to create a text box with the name of last name, you'd have to design all the steps, each holding each one of these, like LAST, NAME, semicolon. You'd have to have registers open, hold those values, then you would have to write this text box, and you'd have to put the shadowing in it, and the events, etc., etc. Now you just drag it on there and drop it. The IDE takes care of that for you. This is where I say most people will spend a lot of their development time is in IDE. So, before you write a program, the very first thing you should do, if you remember from the software engineering, is have a list of requirements that are signed off that everybody agrees to. That's not listed up here because it's more important that you never write code without requirements documents. Otherwise, you're going to be chasing your tail, and it's just going to be an exercise in frustration. So, other things, you need to know how the program works. You need to know the language. You need to know really how the IDE works. You do this by practice, by studying, by going out and taking classes, by watching other people program, following along in tutorials. The only way to really know a language is to actually get into that language and start developing with it. Now, usually you'll start off with like a hello world program, but really what you want to do is you want to say, well, this is a problem that I have. What's the best way to solve that? Find the language that you want to start developing in and try to develop a solution to a problem. Otherwise, you're just going to go out and say, oh, well, I needed to learn this portion of the language. You follow along with somebody's tutorial and you move on. So my suggestion to you is try to find a real world problem that you want to solve and solve that problem with the language. It's going to be a lot of frustration at first as you're learning the syntax and the rules and how everything works. But believe me, with some time, some patience and practice, next thing you know, you're going to be banging out code quickly. You're going to be, knowing some of the tricks of the trade. Also know that a piece of advice I can give you is the programming languages today are so big. Like Java and C#, they're huge, and as they bring out new versions of these, they add more and more functionality. Do not try to memorize everything about the language. It's more important that you know how the language works, so when a new concept is introduced, you know how to work that concept in the language. You're not stumbling over, well, I don't understand the syntax. You understand the syntax, and you can look at it and say, oh, I see how this new feature works. That's great. So I want to distinguish between those. That's why we have Google. That's why we have Stack Overflow or Stack Exchange. That's why we have Microsoft Docs. That's why we have Java Docs. Those are good resources you need to learn how to use in order to solve a problem. So don't try to memorize everything. You're going to get frustrated. You're going to, there's so much there. I mean, the standard install for .NET right now is almost 4 gig, up to 9 gig on some of them, and there's so many things to learn. So learn how the code works, learn how the syntax and the structure works, and then as new features come along or new classes come along, you'll know how to implement them, but don't try to memorize them all. And again, like I said, it's like learning a foreign language. It just isn't, it comes natural for some people, but you still have to understand the syntax and the rules in order to be effective in the language. So let's talk about an algorithm. Well, what's an algorithm? It's a series of steps designed to solve a problem. And generally what happens, you'll have a large problem, and you want to solve that problem, so you break it down into the smallest tasks possible, called subtasks, that can, and remember, computers are great at doing the same thing over and over and over again. That's what they're built for. So to look at this large task, you can look at it, and over time and experience and practice, you look at it and say, you know what, this task is really 4 small subtasks. And so we've got this task 1, 2, 3, and 4. And then you look at those tasks 1, 2, 3, and 4 and say, you know what, we can break task down even further into task 1A, 1B, etc. That's what, when we talk about software engineering, that's what Agile is trying to do. Take this huge task and break it down into small, manageable bits of code that you can get done quickly. Now, part of that, of course, is the architecture of the software. Some software lends to that, architectures lend to that better than others, and some don't. And so another concept here that we don't talk about is the architecture. There's different architectures. There's been client-server, N-tier, microservices architecture, API, REST API, API architecture, decoupled, etc., etc. Based on those architectures out there, you can break your tasks down into smaller and smaller chunks. And so the smaller the task, the more likely it is that you're going to write better code that's easily testable, that's not going to fail, that's going to be hardened. And so as you get into your career, understanding how to identify these subtasks and breaking them down is kind of an art, kind of a just trial and error. But again, with an algorithm, you're going to get this requirement that says do this, and it may seem to be overwhelming, but chop it up, get your subtasks. It's a logical solution to a problem, because remember, computers are logical. And so this is how we're going to solve it. Step A, B, C, D, etc. And that once you get all those steps and subtasks, then you're going to convert it into a statement. And once you've got those converted into a statement, that's your algorithm. Now it says pseudocode is often used. To be honest, I haven't used pseudocode for 10 to 15 years. Generally with the new architectures and software, once you've identified the problem, broken down into subtasks, you can generally get those subtasks defined and programmed without having to write any pseudocode. So what is pseudocode? Well, pseudocode, by the definition, pseudo meaning fake, it's kind of it says it's a readable description of the program in human language. Really what this is programming notes. They go over templates in here, and everything. I really don't excuse me, advise you taking a lot of time with pseudocode. If you're going to write the pseudocode, why not just take the extra step to write the code? So really what I've done, what a lot of the shops that I've worked in, is you create comments. Those comments then give you reminders of how to write the code. I don't write pseudocode anymore. It seems to be a lot of extra time and wasted steps. But know that there's no formal rules, and which is a problem, because then you've got somebody writing it this way and somebody writing it that way. It says practice provides necessary skill. I would suggest that you spend more time practicing the code than the pseudocode. Again, to me, I just think that pseudocode is kind of one of those old remnants from older days, like with waterfall development. So here's a temperature conversion chart. This isn't pseudocode. This is really a conversion chart you can find out there. So for instance, 0 Celsius is 32 Fahrenheit. We've all seen these. We know what these are. There's nothing mysterious about this. So we're going to use this. We're going to convert from Celsius to Fahrenheit. So we're going to use this chart to do so. So here's the pseudocode. And so you start the Fahrenheit to Celsius and Celsius to Fahrenheit. These are well-defined codes. 5/9 times Fahrenheit temp minus 32, and then reversing that is 9/5 times Celsius plus 32. There's no reason to write down these formulas. They're everywhere out there. If I was to have to write this, I would say use Fahrenheit to Celsius conversion to convert from here to here. But again, that's a note in front of a function. And it says after the formulas are proved correct, which in this case they are, you then go through all these steps. Get the input, calculate, and display the results. So this is their example of some pseudocode. And just by looking at this, I would look at this and say, well, why am I writing this in pseudocode? I could do this. Do you want to perform the conversion? If yes, then do this. And which one do you want to do? And if no, then exit the program. And for Celsius, get this, and temp, Fahrenheit, etc. All of this to me it seems to be a waste, because just write the code to do this. Maybe write your steps down. Say prompt for a conversion. Which one do you want to do? Write the methods to do Celsius or Fahrenheit, and then display the data, and then go in and actually write the code. Don't ask the users for the temperature and Fahrenheit. You don't have to get down to this much detail. This is, again, my opinion. It just seems like this is a huge waste of time for something even this trivial. Again, just pick out this is what you want to do. Do you want to convert it, get the input? Do you want to convert to Celsius? You want to convert to Fahrenheit, display the results, and then write the code to do it. So, what's the best algorithm? Well, that's a hard question. So they use this example here, how to get to Disney World, and this is only 4 of them. Fly, drive, hitchhike, walk. There's other ways that you can get to Disneyland. You know, um, each of them have advantages and disadvantages. This just comes, the algorithm that you decide to use will come based on experience, based on, there might be an algorithm that's already defined for you that you have to use. But a lot of times, you're going to say, well, how do you want to get to Disney World? Well, I want to fly. Okay, so flying's the best way to get to Disney World. So you use that algorithm and then come to find out that it may not be the best algorithm to get to Disney World. It may be that driving was better. Right now there's a flying restriction going on. That doesn't mean that what algorithm you chose was the wrong algorithm. Things change. There's a lot of things going on that are outside your control. But when you make that decision to use that algorithm, you're using it based on your knowledge, your experience, and the insight that you've gained from others or from reading online. So you're going to say, I'm going to use this algorithm. So don't be paralyzed by trying to decide which is the best algorithm for something. Sometimes there is a best algorithm, but if there's not a best algorithm, a lot of times you're going to choose one and it may not be the right one. The mature and the senior level developer will look at that and go, well, that's not what I wanted as the end result. It's not the best. And there's 2 decisions. You can either try to continue to force it to be the best, or you can rewrite it or use a different algorithm to get to a better solution. It's that pivot point, as they call it, of making that decision of continuing forward with what I've decided to try to prove that it's right, or pivoting and saying this isn't right, I need to do it a different way, and writing code that's more effective is what I think helps separate a junior mid-level developer from a senior developer. So how do you test an algorithm? Well, you can try to test before typing the programming code. Some of this is not possible. For instance, pretending to be an end user who's not knowledgeable about the program, I have to laugh about that, because how can you pretend to be somebody who doesn't know the program when you're the person who writes the program? This is a problem I have here with this testing of the algorithm. You already know what it is. You already know what your algorithm does. So for testing of that, and you to suddenly just pretend you don't know, that's unrealistic. That's just something that's not possible. So really, if you're going to test an algorithm, it's best that you don't test it yourself, that you get somebody else who isn't knowledgeable about the program if possible, or in the QA department. Otherwise, you're going to test an algorithm that you already know. You've got prejudices built into you because you're human, and so you're going to want that algorithm to succeed. It's natural for us to want that to succeed. So it says putting yourself in the user's shoes helps predict possible mistakes. Again, it's asking us to forget what we know, or to test this based on somebody else. It's just not possible to do. And so that's one of the pitfalls of software development, is if you're expected to test your own algorithms, a lot of times you know what they call the happy path. You know how the program works and the expectations and the results are. So you're not going to test it thoroughly. You're going to test it. It says, yes, it works. You're going to want that to work and succeed. So those built-in prejudices will come in, whether it's intentional or not. That's just what happens. So hopefully you land in a spot where you can have a QA department who's not affiliated test it, or somebody else who isn't affiliated test it. So testing this algorithm using these 2 methods, I would say, should be the very, very last resort if you cannot get anybody else, even another developer who may not necessarily be on the project, ought to at least look at it. But if you're just going to rely on yourself using these 2 methods, understand that these should be the absolute last 2 choices to test an algorithm, because in the end these are the 2 poorest ways to test an algorithm, because they're asking us to do something that humans are not really accustomed to doing, putting our prejudices aside, putting away our knowledge that we've gained aside, and pretend that we're something else. So I just wanted to say that for testing an algorithm, the best way to test it is see if somebody else can help you test it. So the syntax, we have syntax. This is the rules. Learning a foreign language. This is the rules that you have to learn. Spelling, for instance, how you type a sentence in English is a little bit different than how you type a sentence in Spanish, for instance. So this is how you're going to take your algorithm and you're going to translate it into a program. So you're going to have different things out. These four ingredients here that they talk about is pretty universal. So when we start looking at the programming language, things like variables, operators, control structures, objects, those are pretty defined with all programming languages. There's others as well, but usually you could say, hey, control structures are usually while loops or if statements, for loops, etc. And those might be done differently in each programming language, but they're still called a control structure. Objects are objects. It's a basis of object-oriented design. Objects have properties, methods, and events. By definition, is an object. But how you implement those objects or inherit them or encapsulate them is done differently syntactically, but the underlying concept is the same. So when we talk about a variable here, and we're going to talk about it in the Java language, a variable is a variable in every single computer language. How it's declared and used may be different with the syntax, but the definition is the same. So let's talk about a variable. A variable is a placeholder in memory to hold a value of a specific type, whether it's a string, integer, whatever the language will support. But it's named, and it's usually given a name that you can easily identify. So instead of having to know where that variable or that value is held in memory, you just know the name of that variable. So for instance, you might create a variable called total, and you'll know that total contains, it's a memory address out there that will contain a value of some sort. You don't have to know where the memory address is, much like back in assembler where you have to move it into the registers. You don't have to. It says the programming type determines the variable types needed, and much deeper discussion about variable types that integers or longs, etc., is out of the scope of this class. But note that when a variable is defined, a data type is specified. And so when you create a variable, you usually give it a specific type. Now, the advantage of this, of course, is you can locate the contents of that address by the name and use it everywhere in the program. A variable is nice because now instead of having to write, like I talked about earlier, to deposit money from $10 to $20, you don't have to write a piece of code for $10 and $10 a penny and 2 pennies, etc. You can use a variable called amount and put that amount that can differ into there. So it allows a location in memory to be used for different values and allows those values to change. And then, of course, there's no need to know where the actual hardware address is. You don't even care. You just need to know the name of the variable. And then you give what they call an identifier, which is the name of a variable. Now, each programming language has different constraints on the identifier. Some will allow numbers, some will not. That, again, depends on the language. But that's the syntax. You just learn how to create a variable in that language, but know that the variable is a name for a corresponding memory address where values will be stored. Now, for naming conventions, you're going to see a lot of naming conventions out there. And some have stuck around for a while, and others are mandated by the company that you work at. But some things to consider is that you should name the variable with a description of what the variable is either contains or is needed for. So for instance, to create a variable called XYZ and you're in a program and you're trying to call that variable from another spot, you often go, what's this XYZ variable? You might go back up and look and say, oh, it's this. So instead of saying XYZ, say create a variable called deposit total. So that way, as you're developing and you go through it, you look at it and say, oh, what's the deposit total? Or what's the deposit? Then that starts making it a little bit easier, because now you don't have to keep going back up and referencing what that variable is. And on as well as understand that this program you may not be the only person to ever work in this program. You might be the person who's working in this program now, but 6 months from now you go back and look at it, you're going to be spending a lot of time going, what is XYZ? I had a program that I inherited where the person who developed it thought it would be funny to use slang terms and vulgarity for variable names, which, I guess would have been funny if it wasn't so frustrating to develop in, because then I had to go and find out what these values were used for. So use meaningful names. Now, a meaningful name could be something that the company mandates that you work for, but if not, try to, if there's no rigid, set of requirements, try to at least name it something descriptive so you know what's going to be stored in that location. Operators are operators. Generally, it's mathematical operation that can manipulate the data. It can work on numbers. It can work on strings. You might have the same identifier, operator working differently based on strings, or whether it's an integer. So, for example, in Java and C Sharp, on the C-type languages, if you have two numeric values and you put the plus operator, it will add them together. However, if you have two strings, it will do what they call concatenate, or join those two strings together. And so that can lead to some problems. It's to understand that there are certain rules within the development, that this is a good example of them, is depending on the variables that it's working on, the plus may work as either math or concatenation. And there's just really no hard, fast rule about that. That's just something you're going to have to know, and that comes with time and practice of using the software. So be aware of that. So here's some math operators. These are pretty much all the same. You have addition, subtraction, multiplication, division, and then you have what they call the modulus or the modulo, and that's the remainder. So if you have, when you're performing division, a good way that we use the modulus is quickly determining whether a value is odd or even by dividing it by 2. Now, those of you who are going to write a program and determine whether or not and use one of the suggestions, which is area of a circle, rectangle, and whether a value or an integer was odd or even, this is a good indication of how you'll do that. You can use the modulus to divide a number by 2, and if it comes back 0, you know it's even, and if it comes back with any other value, you know that it's odd. So here's a list of standard mathematical operators, which is pretty standard across all of at least the C-type languages, including C Sharp, Java, etc. So there's addition, subtraction, division, multiplication, modulo. Then you have these shortcuts, which is adding two numbers together and then getting the value of that, subtracting them, multiplying, divide, modulus. Now, to do these steps here, actually all of these steps for addition, remember in assembler, it was put this value in CX, put this value in DX, and then do the addition. And here, to subtract and then assign is kind of a shortcut. If you want to take a value of a variable, say in CX, and add 2 to it, you would just do that with this shortcut here. And this is where these high-level languages come into play, that you don't have to give it all the steps and put the value into the registers and then move those registers over and then add them and find out what the values are. You can just use these shortcuts here. So there's incrementers and decrementers. Again, double plus, double minus will increment or decrement by 1. So down here we have this I count. This is the variable. Now remember, we did this in assembler. Remember when we did the increment and we had to put the value into the register and then we had to do the increment on that? Although it's similar, we have here a variable and we set it to 5. This variable is referencing a register, set of registers somewhere, and it's giving it a value of 5. We don't care where that's at, we just tell it where to put it. And now we're just saying that this variable is equal to iCount plus 1. So you can see here that now as we start comparing it back to the old assembler, that this is a little bit more readable than what's going on. And then of course to decrement it, it's the same thing. You have the count and the result, and you put those double minus in the front. So you have pre and post increments, and there is a subtle difference here. The pre operator puts it before, so the increment is here, and this is adding 1 to the variable, or you can do it afterward here. Now, we're not going to get into what the subtle differences of these are, other than the fact that how the variable is updated. This one, if we had updated to 6, from 5 we're going to increment it. It's incremented, and then the variable is changed to 6. In this case, the variable is still 5 and then changed to 6 after. This becomes important in loops and counters. We're not going to get into it here, whether you do post or pre. Just know that you can put it before or after. Now, that's not saying they're both the same. There are subtle differences that you need to be aware of, but that's again for another class. So you have rational operators, or excuse me, relational operators, and this is how things equal or not equal each other. So bang, this is called bang. So this is bang equal, means this is not equal to, less than, greater than, less than, equal to, greater than, equal to, and notice this one right here. For all of you people who are in C, the C-based languages like Java, and I even believe Python to some extent, C#, etc., this is where things are going to trip you up. The comparative value to say, does this or set something, x equals y, to check to see if they are relational, is the double equal. If you use a single equal statement, you are telling the system to set the value equal to the other value. So just know, and those of you who have already started programming, JavaScript's the same way, that single equal versus double equal can trip you up sometimes. So you have logical operators, which is and, or, and not, and we talked about these in the logic. And these are important because these again are comparing two values. If something is not equal, or if something is not this, or something is not this, and or, all of these are done double ampersand, double pipes. This is what this is called, is a pipe here. And we're going to talk about this a little bit, that depending on how you use parentheses, you can check for logicals, for comparing. Again, this is going back to that truth table that we talked way back in earlier chapters. So let's take a look at this really quick. We're going to say if I first number is greater than or equal to the second number, and the third number is greater than the fourth number, and then we say t and t equals t. So that means if 15 is greater than or equal to 10, and 20 is greater than or equal to 15. So this is true and true equals true. This one is false and true equals false. Notice if its first num is less than or equal to second number, and third number is greater than fourth number. Well, if 15 is less than or equal to 10, this is false. That means that this statement here will render the whole statement false, and so it doesn't even compare this second statement here. Now, with true and true equal true, both of these, if, notice the double equal, if first equals second and third equals fourth, then it's false, right? If 10 is equal to, if 15 is equal to 10, well, because 15 is not equal to 10, it's not even going to compare. Most of the languages don't even compare the third and fourth number. And again, not equal and greater than equal to with the ors, saying if this or this are true. Now, the difference here, take a little time on this. It's important for programming. It's a subtlety in programming. If you look at this one, this first, second, third, fourth, and this first, second, or the third, fourth. So what happens here is this is evaluated. If this first verse is true, if first number is greater than second number, then it evaluates the second one. All of these conditions have to equal true. But notice down here, if the first number is greater than the second number, and if this is 15 is greater than 10, then this statement equals true. It doesn't even look at the third and fourth number. It's called shortcutting. And it's important to know, because if you need to make sure that the first and second numbers are equal or greater than or equal to, and the third is greater than or equal to the fourth, you need to use the AND statement to ensure all numbers are compared. So precedence. We have order of precedence. Those of you who have been in math, it is the same. Order of precedence is crucial. This is where your subtle logic bugs will come into play. You will look at something and say, this isn't working. Why isn't this working? It gets extremely frustrating, and that's because your order of precedence is wrong. So there is a hierarchy. So looking at 2 plus 3 times 4, and by the way, there is a question on the final about this because it is this important. You'll notice that it is 14 and not 20. Well, why is that? Because the first in order of precedence is 3 times 4 is 12, then it adds 2. It does not go left to right. It is not 2 plus 3 is 5 times 4. This is an important concept to understand, not only in math, but in programming. And so, again, order of precedence, and we're going to look at that here. So here's our order of precedence. At the very top, we have the increments, and then we have multiplication, division, and modulo. You'll notice that those are before. Notice that increment and decrement are the very first things that happen. And then these are all the same. So if you have something that's 3 times 4 divided by 2, it's going to go left to right. So 3 times 4 is 12, divided by 2 is 6. So if they're on the same plane, then it goes from left to right. So then multiplication, division, modulo, then addition, subtraction, then your comparators here, then your equal comparator. Notice that, and this is what I was talking about before, notice that greater than and greater than equal to are higher in precedent than the equal or not equal, or not, excuse me. And then at the very bottom here, you have your plus equal, your equal. This is your assignment operators down here. So this is the order of precedence. And atop all of that is you can really shortcut that by using parentheses. So what it's not showing here, unfortunately, is that if you put a parenthesis around your addition, then that very top precedence, which should be right up here as a little box, is parenthesis. Anything in parenthesis is done first. Remember that. So we got control structures and program flow. This is where your programs really start to take on a life of its own. Based on the input or based on some changes within the program, your program can take different execution paths. It's almost like a choose your own adventure book. You know, instead of reading it directly from the top to the bottom, you get into a certain end in the page and it says if you decide this, then go to this page. If you decide this, go to that page. And that's kind of what you have for control and program flow. It says what's the order in which statements are executed. If you do not have a good control structure, you get spaghetti code. What's spaghetti code? You take, next time you have spaghetti, and you drop those noodles on the plate, try to find the end of a noodle and trace it through to the very end. And that's spaghetti code. And this was a running rampant. This not only is control and program flow, but it also results in sticking with an algorithm that doesn't work and you just keep bolting things on. Frankenstein method, poor software architecture. A lot of things contribute to spaghetti code, but one of the biggest ones is, depending on how things are executed. So if you're just going to have a haphazardly if statements or repetition, etc., and without any sort of architecture behind it, you're really going to get into spaghetti code, and then you're going to find that updating code in one place breaks code in another place, or updating or changing something in one module breaks it in another, and it's extremely frustrating. It becomes hard and unwieldy, and your code becomes less and less stable, and then as a result, you introduce more and more bugs. So we're going to talk about 4 different control types: invocation, top-down, selection, and repetition, and then how they perform a specific task. So invocation is calling something, and this is where you have a function. It might be a separate class that you import in Java or Python or C that is got specific functionality around it. So in Java, in the base class, you can include the math functionality, and you invoke it by calling it, and you don't have to rewrite it. And that's the nice thing about uh, languages like C Sharp, Java, Python, etc. I'm just going to say programming languages from here on out that allow the addition of external classes or objects to be called or invoked. You don't have to rewrite the code. It it allows reusability because now one bit of code can be used in other bits of code. Some of this can be achieved by invoking a separate API call through like a REST API. So you have a piece of software out there that does some calculations for some reason. Instead of having to write that calculation over and over and over, you can invoke it by calling the API, passing in some data, and getting the result. And so what'll happen is you'll go out and you'll call that, it'll jump out to that other code, execute it, and return back in the original location from where it was called, and then you continue on. Now there are concepts out there of asynchronous programming and multi-threading, which we don't need to worry about. So I just want to bring that up that says the original location of the program may be in a different location, or it may be done asynchronously, but know that you invoke or call that external code, it comes back, and you continue to work on. Well, what's the advantage of invocation? Well, it allows you to break up your huge algorithm into smaller pieces and then be able to reuse those smaller pieces of code in other programs without having to recode over and over. The more you have to duplicate your code, and now let's say there's a change in a tax table. Let's say we're going to calculate the tax, and you have that calculation for tax everywhere, and now you're changing it from 6% to 6.2%. You have to go and find all the instances of that algorithm in your program and change it there. Chances are you might miss one. Where if you only have one object that does the calculation of tax and it's invoked from other portions of the code, then you just change it in the one spot and make sure it runs, and then you move on. So invocation is one of the concepts of object-oriented programming. It is a very powerful way to avoid spaghetti code, to help break your algorithms up into smaller and smaller pieces. Now, some programs like C and old Visual Basic, to some extent, were sequential, meaning that they're all executed in a series from the top down, one line at a time. And this is, it says most common structure, and that's now falling out of favor more and more. It is implemented by entering statements that don't call other pieces of code. So you're saying, oh well, I've got to, do calculate tax. Well, I'm just going to calculate the tax right in line. And now I've got to do add discounts, and you do that all in line. So all of it's done in one piece of code from the top down. And C does a lot of this with sequential programming. Sequential programming is becoming less and less of kind of a structure in the higher level languages, just because there are so many other architectures out there. Now, a selection, standard part. If this, then this. That's a selection, depending on what the values are. And this is something that's more like the choose your own adventure we were talking about. This is what makes your program adaptable. This is what makes your program less rigid. So in a sequential program, if you have a section that, depending on a value, you have to write that in the sequence. Here, you don't have to. You can skip whole pieces of code that don't relate to the value passing in. So for instance, you can say, if the total is greater than 10, then apply these discounts. Otherwise, don't. And so if it comes in and it's not greater than 10, you can skip whole pieces of code. The program doesn't have to worry about it. And then, of course, this is what computer's good for. Looping, repetition. For, while, do, while loops. For each loops is another one in there. A for loop will go a specific number of times that you tell it. You could say, do this for, you could do a for each. Says for each, object in the array or whatever. Or you could say, for I is, 1 to 10, do this 10 times. That's what a for loop does. A while loop will loop, and there's a difference here between a while loop and a do while loop. A while loop checks, it says, do this while this condition is, say x is greater than 1. That means it will enter the do loop and do it once, then check the condition. A while loop will say, while x is greater than 1, do this loop. And so it gives you a way to kind of bypass a loop if it's not needed, or take one operation through the loop, check the value, and determine whether you need to continue repeating or not. And again, based on the language that you use, they're pretty common. This is a great way of allowing you to do the like large amounts of counting or processing. For all of you gamers out there, all a game is a giant loop. While the program is not paused, do all of these things. While the program is, the user is still alive, do all these things. So every time it goes through the loop, it checks for a condition, which can make the, for instance, if your little spaceship or whatever blows up, then the game stops. You're done. And so that's all done in a while loop. So all of these are done while something's happening, and then once that condition's met, it's then I guess the program's terminated at that point, depending on what that condition is. So, we're ready, right? It says here, let's go, let's do this. This is, again, if you're using CS 1400, this is a review. But for those who haven't done any programming, just know that your building blocks are your variables, your operators, which we talked about, and the control structures. So we're going to show some examples in Java in this course, but your programming language of choice will have variables, operators, and control structures based on the syntax of that language. So for those of you who want to do Python, you can download Python. For those of you who want to get into .NET, you can download Visual Studio. For an editor for Java, for Python, and for Visual Studio or C# development, you can download something like Visual Studio Code, which can handle all three of those. So you download it, you enter it, you run it. So now let's talk a little bit about OOP. OOP is a good premise to understand what development is. It is a style of programming. It is still used quite extensively, but it's a different way of thinking about development. It represents items that humans are more adapt to understand, and those items have certain characteristics, worker responses, or as we call them, they have certain properties, methods, or events. So a property here will be a characteristic. So as I'm sitting here looking, I have a can of soda. A characteristic of the can of soda might be that it's made out of aluminum. The color of the can, the size, how many ounces it holds. There are all kinds of properties that describe this. The work, what's the event that can happen? Well, there might be a response, a method is what the work is, excuse me. So one of the work methods for a can of soda is to open. So I have an open method. And that open method causes an event, which in this case would be the releasing of carbon dioxide. but you know, again, this can of soda is an object. It has property, methods, and events. So that's what objects relate to in development. It is what it does, and how it interacts. So in this case, they use an alarm clock. The characteristics, these are the properties. What's the color, the time, the wake time, you know, set a property for that. What's the work that it does? This is the method that it does. It displays, it plays the radio. Again, and then the event, that's what a response is. When that alarm time, that property of alarm time is reached, what event is raised? You know, it plays an alarm. If they hit the snooze button, which is actually a work, then you reset a property and delay for 5 minutes, etc. So they say characteristics, work, and responses. Again, it's properties, methods, and events. That is the common terminology: properties, methods, and events. Most high languages support OOP in some way. You know, you can create an object, you can set its properties, methods, and events, and then you can invoke that object from different parts of the code. The big thing on this is to know that in OOP can represent part of a program as a self-contained object. And that is what's important about OOP. This goes back to that huge algorithm that we talked about. Here's the problem that we have. And part of that was breaking those down into subtasks. Each of those subtasks can be represented potentially by an object. And that object can be self-contained. It has all its own properties and methods and events. You can set its properties, you can set methods. This is what happens when something invokes this object. This is what happens when they hit this particular method. And then it can raise events. The events is how it can communicate back to the rest of the program. You may have a method that says set alarm, and then that alarm, when it's hit, an event that comes off saying, you know, alarm is reached, etc. The nice thing about it is it can be then reused in not just this code, but other bits of code or other programs as well. So now you're maintaining one piece of the code for many responses. Now, that can potentially cause some problems down the road. So as your object becomes used more and more through other pieces of the software, if you're going to change the signature of that object, you have to be well aware of where the other objects are, or where the object is being invoked from. But there's ways to handle that. But the maintainability decreases tremendously. So for instance, going back to that method I was saying, calculate tax. You know, if you have a tax calculation object that has properties, methods, events, and now you have to reset the tax base from 6 to 6.2, you do it in one spot, not hundreds of spots. So it definitely helps with the maintainability of a program, and it helps eliminate spaghetti code. So how this works. This is kind of a contrived example, but it's still, again, trying to not focus in on any specific programming language. This is the concepts that we really are looking at here. So the toy company wants to create a kung fu action figure. So there's a couple of different ways to do this. It can give every employee a piece of plastic and tell them to carve the figure. You know, that's a pretty standard way to do something if you want. Well, what's the problem with that? Well, you're going to have quality control problems. Some people can carve better than others. So you're going to get inconsistencies. And what if you decide that you need to change a certain part of that action figure for one reason or another? Then everybody has to go back and change and try to find their own to change it, hopefully. And so you could see that that is a highly ineffective way of doing that. The second way to do this is you can create a mold, or as they call it here, a class, and then you can mass produce that figure efficiently by using the same mold, the same injection process. You know that you're going to get a better quality, and it's going to be done faster than if you have everybody do it one at a time. So now, instead of having to change, say you decided to change the pose of the figure, you create a new mold and a new process, and now you can use that process. Or let's say that your kung fu action figure is so popular that you want a different pose for it or a different character. Now you can just create a new mold without affecting the original mold, and now you can be creating the same figure in different poses, for example. And so that's the two methods that they're talking about. So we take the mold. How do we make the mold? Well, we have to take the time to do that. So in this case, you're going to give the outline of what the product looks like. It's going to, be in this pose. It's going to be, posable figures, size, etc. It gives the attributes of that. So whatever attributes you set for that mold, every single figure that goes into that mold is going to have a very similar, or should be in theory, the exact same when it comes out. So then to create it, we have to set some events or some methods for that. So we have to pour the plastic into the mold. Well, we want different figures, kind of like Army Men figures. You've got green and brown and gray, etc. So using the same mold, you can just change the colors. You still get the same figure, but now something's changed about it's the color in this case. So now you can take and say, here's the base, a base figure is green, but now you could take that mold and you can create brown figures or yellow figures or red, whatever you want. They still look the same, but now they have an attribute that's different. But again, it's more efficient because now all you're doing is changing the plastic. And then you can put the figure to work, which can perform some action like Kung Fu Grip for those who remember the old G.I. Joe. But those figures can now work once they've been built and once they've had some attributes changed, like in this case the color, but then they can all work the same. So the class here is a mold or template for creating the figure. So understand that as we are using this analogy, that what we're using is now translating this into programming. So the class is the mold. The class is the way that you're going to create the object. In this case, that object is a figure. Now the instantiation of that object in this case is pouring the plastic into the mold. So when you create that figure, or it might even be heating up the mold if that's what you want to think. It's now we're going to use this mold, we're going to get ready to create this. The constructor is used to instantiate the object in the class, meaning that when you instantiate the class, you can use a constructor to say, I want this mold to be created, but I want it to be created at 150 degrees. Or I want this mold, it's the same mold, to be created at 175 degrees. The property of that object is the color of the plastic, in this case. So now I'm going to construct this, instantiate this process, and set a constructor with it, and I'm going to set its property, and then I'm going to start or invoke this method, meaning I'm going to say start the process. Drop the plastic in, heat the mold up, press it, whatever method is used to create an action figure. And then when it's done, the event would come back that the mold opens and out drops the toy, and that could signal to the class, hey, this toy's made, I'm ready to pour plastic into the next mold. And so it lets them know that I've started, I've completed, or if there was an error possibly, like there wasn't enough plastic, you could be notified of that as well. So that's called an event. So here's how we have this kind of the concepts. So you have the class, the mold, which is properties, methods, and events. That's where, again, characteristics, work, and response. Properties, methods, events. This slide here is important to understand. In OOP, you're going to know properties, methods, and events.
Now, that is not saying that every class has to have properties, methods, and events, but that is what defines a class. Then the creation. This is the instantiation of this. This means that I'm going to create an action figure. The end result is an object of class Kung Fu figure. So, looking at this, this is the mold and this is the end result. Well, this is all I care about. So when I instantiate or create this action figure, I create a mold, I set some properties and methods, and listen for events on the creation, and this is my end result. But the nice thing about this is what's great about OOP, is how I create this mold, how it heats up, how it determines, I just say I want a red action figure. I don't care how that's done. That's already been determined by the internal methods that happen when you create or instantiate the object. You don't care how it sets it up. In real life scenario, here they're using this toy, but in a real life scenario, when you instantiate or create an object, it might go out behind the scenes and make a whole bunch of connections to a database. It might make connections to different files and set itself up so that when you're ready to call a method on that, it's ready to go and work. But you don't know what it did. You don't know which databases that it went out to. You don't care. All you know is that when you create this object and call this method, that this is a response you should get back. And again, this helps with what they call obfuscation, how they create this mold. This might be proprietary. There you might have a method out there, or excuse me, an object out there that has proprietary information in it, the secret sauce, so to speak. It's connecting to databases. It might carry proprietary algorithms. And so you create that. You don't care what's going on out there. You just know that you need to call that particular method and it returns you back a value. Or you listen to an event and respond to that event. And that's another big powerful feature of OOP. So now that we talked about the object, there's three different types of how this works. So inheritance. This is creating more specific classes based on a generic class. So our generic class is the mold class. Okay, we want to inherit from that now, and now we want to say, okay, here's the mold class. It has properties that all molds have to use. It has the figure, it has maybe the material that it's made out of, and it may have a couple other attributes to it. Now, instead of saying, I want to just use one mold to create a green or a red action figure, you want to create a whole bunch of action figures in line. So now you can create new classes of those molds and say this one only does green or this one only does red. So that's what inheritance does. It allows you to take a base object and create a more specific object. And so what happens, instead of having to create that mold over and over and over again, you create the mold and you say these are the specific properties I want to set. In this case, the color of the plastic or whatever. And so now you don't have to take all the time to create a new mold for each one. You can just go take a base mold that's already got the figuring and the metal and everything and drop it into a machine that only does red plastic, for instance. You don't have to create it from scratch unique. And that's kind of nice about that. And then you can subclass that, which is an even more specific class based on the parent class created by inheritance. So let's say we have the mold. This is the toy mold. The base class or the parent class, and so this has its own event. Say it has the figure in it and the metal. Let's say aluminum. The base class down here says, okay, we have a base class here, and we want to use the inherit from this base class. And now we want to create a Kung Fu character that's red. And that's what this subclass is. So if you look here, we have a person class. And a person can be an employee, a student, or a customer, right? I mean, a person, and the higher up this is. So a person might have some, in the base class, might have an identification, gender, some other properties, methods, and events that apply to everybody. If you create a person, you get these properties, methods, and events. And then you can say, well, now I want to create a customer class. Well, a customer class has additional information in it that's unique from a student. A student might have a student ID. They may have, a teacher. There's information that pertains just to a student. There's information that pertains to a customer. And then you'll have an employee. And under an employee, then you'll have a manager or a salesperson. A manager might have properties, methods, and events that allow them to have access to all the salespeople's salary or sales figures, etc. Where a salesperson would only have information related to themselves. So you can see if you create a manager, you're going to create an employee object which inherits from the person object. What this does is this allows me to get more succinct in what my specificity of the object is, but because it's inherited, I still gain all of the properties, methods, and events from person and from employee, and then I extend it for a manager. To encapsulate, and the last, so you've got inheritance, encapsulation, and polymorphism. Those are the three pillars of OOP. We just talked about inheritance and its and how powerful it is, and we're not going to go into much of these other encapsulation, polymorphism. There's a whole class about this, but know that encapsulation can obfuscate the operations from other objects. This is what I talked about. This is hiding your secret sauce. This is allowing you to create a sealed class that has all the special functions and formulas in it, and that people can call that or create it, but they don't get all the secrets behind it. Polymorphism is just to be able to use the same expression for different operations. So you might have, you can polymorph this employee now to have a manager and a salesperson. Even though they're the same, you can change what their functionality is based on how you set up some specific methods. You can polymorph this to say now this employee is a salesperson. So choosing a programming language. This is a question I get all the time. Well, which programming language would you choose? Well, in the good old days when I was a junior programmer, I had my programming language, and I'd live and die by that programming language and jump into the fray and argue about which one's best. That today is, there's still people like that, unfortunately. But today, it's functionality. The big one's vendor stability. You're going to see programming languages come and go. How long's that language been around? How well is it supported? Who's supporting that language? I don't know if I'd necessarily say popularity is great for choosing a programming language. What's popular today may be not popular tomorrow. Kind of like fashions and trends. Those can change. The job market, I think, is probably the biggest one out there. Ease of learning. Okay, ease of learning is something that if you're new to programming, that might be a factor. But understand, if you understand the tenets of OOP as you're learning about it, and sometimes it clicks, the ease of learning is not necessarily a good indicator for me. The big one is the job market. That's ultimately what I'm going to be doing with my career, and so I need to know what the job market states. The job market is saying that this language is up and coming, then like Swift or Object-C, maybe I'll go and learn that. So all of these should be some sort of a function to consider. Price isn't necessarily as much of an object now. Most companies are more than willing to get you into a language for free because they want to, get that language out there, and they want you to use their tools or etc. Performance, again, is a big one as well, but that's becoming less and less of an issue unless you're looking, like I said, to get down to the bare metal. If you're looking for assembler, if you're looking to specifically write in C for a reason. Now, some vendors may require you to say, look, if you're going to use our hardware, you only can use these languages. But the nice thing about it is there's trials out there. You can download, the big ones, Java, C#, Swift, Object-C, Rust, all kinds of things like that, Python. You can download them and try them for yourself. Some of them you might like, Say, I really like this, and others you may not. So a couple of things. Number one, computers are stupid. Garbage in, garbage out. They do exactly what they're told. So blaming the program failure on the programmer, not the computer. The computer's doing exactly what it told. Unless you happen to find some sort of a hardware glitch, most of the time if the program fails, it's because the programmer had a problem. So again, I love it when my kids are playing a game and they're losing against the computer, and they say it cheats, and I'm like, oh yes, somebody somewhere wrote the program just specifically for you at this time, right? That's not how it works. Computers do exactly what they're told. So that key word is responsibility. We are responsible for the programs we put out. I've gotten to the point in my career where I want to start making more of an impact in the software that I'm putting out. It's more than just a paycheck. It is changing people's lives. It is helping people, or making some change somewhere. And that has ramifications. You put that software out there and it's not a quality software, or it's full of bugs or errors, it is potentially life-threatening in some cases. So take responsibility if you want to program. I love programming. It's great. I love solving the problems and breaking them down, and watching people use the software, and making their jobs easier, their lives easier. I mean, it is a fact that if your software is easier to use, people are going to have a better attitude about it. And if they have a better attitude, it can affect other parts of their life. So, bad software is just, it hurts everybody in the IT industry. So, a couple of things, summary up on this. A program is just a collection of statements telling the computer what to do. Different languages types. There's the low-level language, machine language, again, zeros and ones. Hardly anybody programs. Low-level languages, the lowest level of that is assembly, and right above that, C. If you're going to be in the low level, try to stick with C. It's a little bit easier to program in, a little bit more familiar. And then you have the high-level languages such as Java, C#, etc. And use integrated development because it gives you tools, it helps you with syntax checking, helps you get your job done better. Notice that the structure is an algorithm. Your algorithm is your final end result, but you want to break those up into subtasks there. You want to make them manageable so that as you create, look at that and say that can be an object. As we talked about in OOP. I don't necessarily adhere to the pseudocode representation here. A program structure to me is better represented with a flowchart like we talked about in the software engineering. But all programming languages have variables, operators, control structures, objects. Know and understand operator precedence. That is the big thing on this slide, 61. Like I said, there's a test question about it. That's how important it is. This is where bugs come in, and this is where frustration can abound if you don't understand operator precedence. Avoid spaghetti code. How do we do that? Well, architecture solutions. Use OOP. Try to avoid just using repetition in your code. A good indicator that you maybe need to create an object is if you find yourself writing the same bit of code over and over and over again. Try to avoid doing that, because every time you write that code, you have to make the change in, say, computing an algorithm for tax, then you've got to find it everywhere. And once you get your spaghetti code going, it then becomes uncontrollable, and you end up spending more time chasing down bugs and trying to fix it than doing the exciting stuff like adding new features and being innovative. Know the invocation, which again is invoking something. That's calling an object. There was the sequence, there's selection, and then there's looping. To start programming, create a package, the one of your choice. It may be school, maybe work. Choose an editor, write code, and fix and learn from your mistakes, and keep plugging at it, and go in this loop. Okay, I've learned some of the basic syntax, I've gone through the help, now I want to solve a problem. What's my problem? If you're finding that you have a problem that you want to solve with programming, you're more apt to dive in and learn it than just looking at a online tutorial and then quickly forgetting it. Also remember, in programming, don't get so hung up of trying to memorize all the syntax and all the nuances of a language. That is what Google, that is what the docs are for, that's what Stack Exchange, etc. These languages are getting large and they do a lot of things. It's better to understand how to find the answer, and once you see the answer, how to syntactically put it into your code than trying to remember everything. Understanding how your code works, how the syntax works, how the base works is more important than trying to memorize all the features, at least in my opinion. Notice again, object-oriented. You have properties, methods, and events. Here it says characteristics, works, and responses. Properties, methods, and events. Those are what define an object. And object-oriented programming, the three pillars are inheritance, encapsulation, and polymorphism. There are other classes that you can take that go into more depth in here, but understand that object-oriented programming will save you time, will save you money, will save you coding headaches, will allow you to make your code more extensible and provide a much better coding experience than a sequential spaghetti-coded nightmare. So that's it for chapter 14. In the next chapter, we'll continue on with actually looking at some code that and putting some of these tenets into place.